Okay, so now we have solved for our big X of x, and so if we recall the things that we did up to now, okay, we obtained these two ordinary differential equations using the separation of variable technique, and then we solved equation 1 for 3 different lambda values, for positive lambda, lambda equals 0 and negative lambda. And it turns out that when lambda equals 0 and when lambda becomes a negative number, big X of x equals to 0. The only non-trivial solution that we obtained for big X of x was when lambda equals to a positive number, and in this particular case we got big X of x equals to b3 times sine of ax, but we found that a equals to n, and here n is an integer. So at this point we do have an expression for big X of x. Of course we do have an unknown b3, that is fine. So the next step is to solve this first order ordinary differential equation with constant coefficient. Now in this equation our unknown is big T, and we all know the solution for this one. The solution is big T of t equals to some constant, let us say C3, times e to the minus of this, so minus lambda t. That is the solution. Great. So now we can construct the solution for u of x comma t. And remember, we took u equals to big X of x times big T of t, and if you do that you will get this term times this one. So you will get b3 times c3, which is a constant, let us say d, times sine of nx times e to the, by the way, so lambda equals to a squared, but a equals to n, therefore lambda equals to n squared. So instead of this lambda, now I can write n squared t. So as you can see, this side depends on this constant d, at the same time this depends on your integer n. Okay, but remember, this the solutions that we have now satisfies both boundary conditions, but we never use the initial condition. Now let us try to use the initial condition to figure out the value of d. The initial condition for this particular problem was u of x comma 0 equals to 1, and if you evaluate this, the solutions that we found at time t equals 0, you will get d times sine of nx times e to the negative n squared times 0. Okay, and this one must be equal to 1. Okay, so let us think about this. So this term is 1, because here we have e to the 0, therefore it is 1, and now we have d times sine of nx. So this is a function of x, and d times sine of nx equals to 1, and we know that d is a constant. Can we find a constant which satisfies this equation? In other words, can you give me a value for d where this d times sine of nx equals to 1? It is not possible. Okay, but let us think about this one. So here we have d times sine of nx times e to the negative n squared t. So what does this mean? This means for each n value I have a solution that satisfies the boundary condition. So as an example, when n equals 1, when n equals 1, let us say my solution is u1 of x comma t equals to, let us say, some constant d1 times sine of, now n equals to 1. So, we have sine of x plus e to the negative t, because n squared is 1. Similarly, we can get a second solution with n equals 2. Let us say here you have constant d2 times sine of 2x times e to the minus 40, and so on. And each of these solutions satisfy the both boundary conditions. And our original PDE was a linear one. So, from the superposition principle, we can construct a new solution using the linear combination of all of these solutions. So, let us say you have big U of x comma t equals to sum of these solutions. Okay, let us say it is dn times sine of nx times e to the minus n squared t. Again, all of these satisfy the boundary conditions, both boundary conditions, and because since our original PDE is a linear one, then from the superposition principle, the sum of these solutions will give you another solution that satisfies both boundary conditions. Okay. Now, let us think about this. Now, let us try to figure out the value of this dn using this solution. Okay. Now, if I substitute t equals 0, then you will get summation n goes from 1 to infinity d sub n times sine of nx. Here we have e to the negative n squared times 0, and my initial condition says this equals to 1. That is the initial condition. Okay. So, now this is 1. So, basically we have summation n goes from 1 to infinity of dn times sine of nx equals to 1. Okay. So, I hope this equation is familiar to you, especially the left hand side. Now, if you think about this left hand side, this is a Fourier sine series. This Fourier sine series came from a function, a periodic function, odd periodic function. And what is that function? That function should be 1. So, now using the Fourier technique, we can figure out the value of dn. And remember, our x goes from 0 to pi. So, if you think about the odd function, let us say this is 1, x goes from 0 to pi, x goes from 0 to pi, yes, and let us construct the odd function for this. So, then it should be something like this. Great. So, now we have a periodic function, periodic odd function. Okay. So, this is your interval. Your interval goes from negative pi to pi. So, if you think about the Fourier series, then your p value should be pi. Then these Fourier coefficients d sub n can be calculated using the following integral. So, basically we have 2 over the value of p, which is pi, times the integral goes from 0 to p is pi, okay, and f of x. So, in this case my function is 1 times sine of n pi x over p dx. We can cancel this pi with this, we have 2 over pi times the integral goes from 0 to pi of sine nx dx. Okay, let us integrate this. Integral of sine nx is minus cosine nx over n, lower limit is 0, upper limit is pi, and in this case you should get dn equals to okay, I am going to write the value of dn in this part. So, dn equals to 2 over pi times negative cosine n pi plus 1 over n. That is it. So, with this value of dn we can construct our final solution. This dn goes here, and with this I finish the first example from chapter 12.3. Thank you.